All right. So let's talk about the two labs. These are completely separate labs, okay? There the two shall meet. I don't want diagrams shared from the two labs. These are like two completely separate entities, okay? So let's start with the inclined plane lab. So the first part of this lab involved you having a block of wood sitting on an inclined plane. So this is the classic example of forces can be exerted on an object, but yet there's no acceleration. So I've got this like this. So what are the two forces acting on this system? Gravity is in the direction of motion. So you've got the gravity mafia trying to hold it down, but the frictional mafia is holding it in place. Okay? You're not accelerating. So one of two things is happening. Either they're just completely balancing each other out, or the frictional mafia is actually bigger force than the force parallel. So what I could do is say, okay, all right, here's the inclined plane, and you calculate the force friction. And let's say that your force friction is, I don't know, positive 3 newtons, okay, whatever that is. And then at that same angle, the force parallel was negative 2 newtons. So if you had a positive force friction of 3 newtons and a negative force friction of 2 newtons, what would be the acceleration of the system? Do not make this different. 0. Why? Friction's holding it in place, okay? This is what's happening right here, right? This is what's taking place. The frictional force is holding it in place. You're not accelerating. Now, if I take a cart and put it at that exact same angle, I get a massive acceleration. I put a wooden block here, I got nothing, okay? I got nothing, all right? Dramatic pause. But if I lift it up, eventually what's going to happen?
It'll accelerate.
Because what am I making bigger?
Force parallel.
Making the force parallel bigger, okay? I'm making the force parallel bigger. Now, interesting thing happens though. If you look at force friction equaling mu times force normal. As I increase the angle, what happens to the normal force? Becomes smaller. Because less and less and less of that weight is acting into the board. More and more of it is going into the force parallel. So as I lift it up, if you assume that mu remains constant, your force friction is actually becoming a smaller number. So your force friction is becoming a smaller number, but as you lift it, what happens to your force parallel?
Increases.
It gets bigger. Now, here's the key assumption for static. Listen to the one key word of this. Here's the key assumption for static friction. Is that at that point where it just begins to slide and land on your foot, God, that hurt. Oh, the edge of the board caught me right on the inside of my ankle. Oh, okay. So at that point where it just begins to slide, we assume that the force parallel equals the force friction. Okay? They balance each other out. It's a tug of war. It's like, okay, we'll begin to move. So since mu equals force friction over force normal, force friction is the same as force parallel, so that's Fg sine theta, Fg cosine theta. Yay for trig functions. The only time you use it outside of a classroom, mu equals tangent theta, but that is only for static friction on an inclined plane. Okay, that's it. It's the only time it works. Kinetic does not work. So what that means is that when you start doing the calculations for the second part of that lab down below where you were pulling it up at a constant velocity at 30 degrees, what happened in the static stays in the static. Don't transfer that coefficient of friction down. Do not transfer anything down. It's a completely separate deal. Now, once you get it on that 30-degree angle, so let's talk about that. Curse the block. So, you got a 30-degree angle. You've got your force diagram number 1 should be drawn at a 30-degree angle. Okay? You can do it on the back side of the lab. It should be drawn at a 30-degree angle. You can't randomly pick it. No, it only works at a 30-degree angle. You should have your gravitational force, some force parallel, some force normal, some force applied, and then some force friction. Okay? 5 completely separate vectors labeled. So here's the first thing I'm going to check when I get to grading this part of it. I'm going to tell you straight up. What was somebody's force applied when you pulled it up at a constant velocity?
2.5 newtons.
Exactly 2.50 newtons.
Yeah.
Okay? If that's your applied force, here's what I'm going to check. Is that when you add together that force parallel and that force friction, these two values better add up to 2.5. So these two, force parallel, force friction going down the inclined plane, those two added together have to balance out the force applied. Yes?
If it like already added them and just did one line, like
That's
so
fine.
zero minus one.
I prefer that you have two
No, I'm thinking this one was harder.
because it's two separate forces.
So then it's like 21. That's an extra
Okay.
one. This one.
Cool with that. Now, make sure that that you show me all of those calculations, okay? I really don't want to try and guess what you've done because I'm not, okay? Show me all the calculations. All right, so let's talk about the 3 problems down below. So the first one, this should be old school. We're just figuring out how much force it takes to pull something up at a constant velocity. So that first problem, the answer to that, should be something, listen to me very carefully, something close to the legal drinking age. Okay? Not what it is during prom weekend.
19.
Okay? Legal drinking age. Now, when you get to problems 2 and 3, and remember this in terms of the lab that you're going to start today. You're going to do the exact same calculation that you started off with on problem number 1. You're going to figure out how much force it took to pull that thing up at a constant velocity. Okay, and if all goes well, this is a huge ish, but the force to pull it up at a constant velocity should be around 4 newtons. Okay? It's an ish, it's around 4 newtons. So on problem number 2, the bottom of that inclined plane lab, the force, not the mass, the force should be around 4 newtons. Okay? So there's 2 ways that you can generate that amount of force. Option number 1, you take your hand, you hook up a force meter, and you try and pull it and maintain a constant force of 4 newtons. Okay? You could do it, but that's tough. Okay? Because you got to pull with the same amount of force all the time, like, maybe yes, maybe no, probably not. Or you go, cool, we're on an Earth that has a gravitational field. Let's let gravity do the work. So then you come out here and then you have to figure out, well, how much mass do you have to suspend from the end of that string to generate 4 newtons of force? Okay? Now, let's just play the hypothetical game. What if you needed 9.8 newtons of force? 1 kilogram. Why? Because 1 kilogram weighs 9.8 newtons. If you needed 4.9 newtons, you'd use a half a kilogram, right? So to figure out the mass, what are you going to do? You're going to take your number and divide it by what? 9.8 meters per second squared. Okay? So this is an ish, but your answer number 2 should be around 0.4 kilograms. Okay? It's an ish. It's somewhere around in there. Now, when you get to number 3, Number 3, I've given you the exact same masses, the same angle, the same coefficient of friction. What's the only difference between 2 and 3?
We're going down.
Which way friction is going and which way the block is moving. So, to kind of give you a visual, here's what's happening. So on problem number 3, okay, you're letting it slide down like this. Now, when I set this problem up, why did I have to make the force parallel bigger than the force friction? Yeah, because if the force friction was bigger than the force parallel, what would happen?
Nothing.
It just wouldn't go anywhere. It's like, well, Bergkamp, that's a stupid question. How much mass do you need? None. Because friction's going to hold it in place. Okay? So when I determined that coefficient of friction, I had to come up with the coefficient of friction where the force friction was smaller than the force parallel going down. So it's the same idea. Here's the setup, but you're still, and this is sometimes conceptually a little bit tough to get. Pulling it up is easy to see that you're pulling it up, and that's the direction of the force. But in this situation, you're still pulling it up. You're applying an upward force, but it's sliding down. Because what you're doing is that you're providing the force to keep it from sliding down. So you're applying an upward force, but it's still moving down. Okay? That makes sense. So that would be like me lowering this. The motion is down, but I'm still applying an upward force. Okay? Any other questions on the inclined plane lab? Are we good with that one? Okay. If you have done another diagram if you've done that diagram on another sheet of paper, just staple that to that lab. Okay. So we're done with that one. That's completely done. Okay. Done. Finished. Okay. Now the hanging sign lab problem. Here was the basic idea of what you were trying to validate, basically. So you had this force pulling down at negative 9.8 newtons. Okay? Cool. Was it accelerating? Start with that basic idea.
No.
No. So all the forces, you know what the drill, they're going to add to
Zero.
the goose egg. So this is also the classic example of what happens in the X.
I like pulling it up to the light so I can see through it. You know.
Oh yeah, I do it all the time.
I find it.
So,
Oh, that's
stop. So what happens in the X stays in the X. What happens in the Y stays in the Y. Horizontally, are there any external forces?
No.
No. There's no horizontal wind, there's no swirls, there's no horizontal gravity, which would be weird, okay? It's just the tension, which is the same idea of flying the limb on the moon. If you wanted to go sideways, you have to fire the engines, because if you want to accelerate, because there's nothing else to make it move. Same thing is true as happening horizontally. So the X direction is pretty simple. You only have two of them, X1 and X2. What's the only way they can add up to 0? Is that they're equal and opposite. So here's hopefully what you should see, hopefully, is that when you look at those forces that you're going to find, and you're going to show me the work, because in big bold letters I told you to show your work. Here's the idea, is that when you look at those X components, pick one of them and make it negative. Hopefully your X components are pretty close to each other. I can live with a little off. Now, 5 and 12, not so much, okay? I can live with a little bit off. Now, your y components. Your y components, in theory, should add up to negative, or to a positive 9.8 to balance out the negative 9.8 Newton force that's pulling it down. And like I said, generally you get pretty close, okay? All right? Maybe not exact, but you should be pretty close. So make sure on that, you only have to draw one vector diagram for the hang the sign left. When you get done, it should look something like this. Two opposing triangles at negative 9.8 newtons, drawn to scale with a correct angle. Show me what the scale is. On this one, you can easily probably just let 1 centimeter equal a newton. Okay? Makes the math pretty easy. Make sure that you have labeled them like YX, YX. If you want to call that tension, force, whatever. Okay? Just don't randomly draw them. So this is what that should look like when you get done. So hopefully what you see on the next part, when you increase the angle. When you increase the angle, are you increasing the values of the y components?
No.
No, those stay the same. Why? What do they still have to add up to?
9.8.
Negative 9.8. So by increasing the angle, what are you making bigger? The horizontal components. Okay? You're making the horizontal components bigger. So that's what you should see, is that when you get to that next one, that the horizontal components have gotten bigger, and the sum of your vertical components should still be staying at about 9.8. Okay? Cool with that? Got that. Now, let's talk about problem on the back. And this is 30 degrees. So, this is what I would do if I were you all. You know, this reading on the scale is 20 newtons. That's the hypotenuse. So the hypotenuse force vector is 20 newtons, okay? It's not the vertical, it's not the horizontal, that's the hypotenuse. What I would do first, personally, is that I would work off of that 60-degree angle on the outside. Because to me, it just makes it easier to see and it's less muddled, okay? I would work off the 60-degree angle. You don't have to. You can work off that 30-degree angle and work on that inside triangle. That's great. If you want to do that, it's great. You're going to get the same answer. It's just a matter of how you choose to do it, okay? So, this is the hypotenuse and you know the angle. So, this vertical component over here is about 17 newtons, all right? But this thing weighs 30. So it would be like this. I owe Isaac 30 bucks, okay? I owe him 30 bucks. I've paid him $17. How much do I still owe him? 13. How'd you get it? Yeah, subtracted it out. Because these two values here have to add up to 30. So once you find this vertical component over here using trig functions, this is going to be 30 minus that y value. Okay? Now, when you get this x component, which not ruin the surprise, is going to be 10 newtons. Oh, no, no. So if that's 10 newtons, what does this, the other side have to be? Negative 10. Or I don't care which one you make negative. Okay? Really doesn't make any difference. You got positive 10, negative, I don't care if you get one. just so that they add up to equal to 0. So at this point, you're going to have the two sides of a right triangle. How are you going to find the hypotenuse, which is the reading on the scale? Pythagorean theorem. Hey, a squared plus b squared equals c squared. Then, and again, depending upon how you want to work this, if you want to work off this outside angle, you can do inverse tangent of y over x. But this is going to get you this angle out here. The problem actually asks for the angle in there. So, your answer to number 6 is probably going to be a little bit less than your current age. And the angle is going to be around 40. Man, 2 KB shirts side by side. I can't handle it.
He's a Nebraska fan too, he's a poser.
Really? Okay. Everybody cool with that? Now, let's talk about the next problem on number 7. So here's this 8,000 Newton I-beam. So let me kind of take you through the thought process. If you were only lifting it with one cable, how much tension would there be in the cable?
8,000.
8,000. Right? If you only had one cable. And if it weighed 8,000, that cable would have to lift all of 8,000. Right? But what if you had 2 cables and you lifted it like that where the cables were vertical?
4,000, 4,000.
Each one of those would be 4,000. Right? So no matter what does the sum of all of the vertical components have to add up to?
8,000.
8,000. So what you did is that you tied it with rope like this. Okay? It makes it more stable. You're lifting a big, massive I-beam. You don't want to generally hold it up with just one cable, okay? Because if it tilts at all, bad things happen. So this provides a nice, stable environment to lift this thing. So you're told that the angle between the I-beams and the cables is 70 degrees. That's the angle that's 70 degrees. Because you're told it's between the cable and the I-beams. Okay? That's the 70-degree angle. So, here's the big question. Even though there's 2 cables, are the vertical components of each side still 4,000 newtons?
Yeah.
Absolutely, right? That's still 4,000. So what are you trying to find from a geometric standpoint? You're trying to find the hypotenuse, okay? So right away, if you're trying to find the hypotenuse, and one side is 4,000, what do you know your answer has to be bigger than?
4,000.
4,000. If not, you've torn the fabric of space and time. Nice, cool, don't get me wrong, okay? Use your power for good, not evil. So your answer has to be bigger than 4,000. Because if it's not, bad things are going to happen. Okay? Got that one. Cool. Green. Now the last problem. On number 8. Number 8, conceptually, is the exact same as number 6. It is literally the exact same idea. There's 1, there's 3, there's 2, and this is a 45-degree angle. And that's a 20-degree. So, here's the story. The system is in equilibrium. Y's add up to Y's, X's cancel each other out. So, you're told that block 1 weighs 15 newtons. Okay? Weighs 15 newtons. So what that means is that as long as this is a static situation, the upward force here is also 15 newtons, which means over here, that's also 15 newtons. So there's two ways, and this is where this problem here becomes similar to the idea of the inclined plane problem in the mass. I need to generate 15 newtons of force. So either I can hook up a Newton scale and tie that and have the Newton scale read 15, or I can take a rope and a pulley and I can extend a 15 Newton force from the end of the string. No matter what, I'm generating 15 Newton force that's representing that hypotenuse. On the other side, that other one weighs 31 newtons, which means that hypotenuse is 31 newtons. So, once you find the two y components, what are they going to add up to? The weight of what's ever being suspended by block 3. What should you see about your x components? Should add to
0.
Be careful to say, what about your x components? They are 0. No, if your x components are 0, this is weird, because this means you're hanging straight down, which you're not, okay? You can say that they sum to 0. You can say that they add to 0, but you can't say that they're 0. So, down below, this is what I want to see. You have an x component line and a y component line. Let me explain what is not showing your work. 11 comma negative 11 is not showing your work. You wrote down numbers. This in no way, shape, or form indicates that you know what the sum is. Now, if you put 11 plus a negative 11 equals 0, now you're talking my mathematical love language. Because now you're showing that that sum is actually 0. Two numbers written down separated by a comma are just that. Two numbers separated by a comma. It doesn't mean anything. You want to show that what those sums are. Okay? Good with that. Francesca, are we all right?
I was confused on that one. I just don't understand. I still don't understand.
This is 15 newtons.
Yeah.
You understand that?
Yep.
You know that this is a 45-degree angle. Can you find the x and y components using sine and cosine?
Yeah.
Okay? So both of those, let me give you a hint, are 10.6.
They're gonna give it,
It's a 45-degree angle, they're both 10.6.
oh, yes.
Because it's a 45-degree angle. On the other one, you're going to do the same thing. The hypotenuse is 31 newtons. Find those x and y components.
Okay.
These two y components, 10.6 plus whatever you get over here, are going to add together to balance out the weight of what's ever hanging down below. So your weight on number 8 should be very close to the degree angle on number 6. Okay? I didn't plan it that way. Don't think, wow, Burkamp, that's cool that you thought that through and you set up the numbers. No, I did. Completely random. Okay? So the value of your weight on number 8, it should be very close to your angle on number 6. Okay? Staple that diagram to the back of that sheet, but do not staple all the labs together into one big conglomeration. Okay? These are separate labs. Okay, let's stop the camera, please.